Hey! Welcome back to Pixel Perception. So glad you are here.
Last episode was wild. B trees. LSM trees. What are we covering today?
Today we talk about encoding. How you package your data to send it over a network or save it to disk.
Okay. And why should I care? My JSON is working totally fine.
Ha! Famous last words. Leo. By the end of this episode, you will never look at JSON the same way again. Promise. Okay. So, what even is encoding?
Okay, so encoding. What does that actually mean?
So your app has objects in memory. Right. Like a user object. When you want to save that, you need to convert it into bytes. That is encoding.
And decoding is just the reverse. Bytes back into objects.
Exactly. Encoding, serialization, marshalling. All the same idea. And decoding, deserialization, parsing. Same thing. People just use different words for it.
Okay. And the format you pick. It actually matters a lot.
Oh. It matters so much. The wrong format can break your entire system when you update it. That is what this episode is about. Here is the real problem. Things break when you update your app. Let me show you why.
Okay, but like, I update my app. All the old data is still there. Why would encoding cause a problem?
Great question. Think about a rolling deploy. You push a new version of your app. But not all servers update instantly. You have old code and new code running together.
Oh no. So the old code might receive data that the new code wrote. And the new code might receive old data.
Yes. And this is where you need two things. Backward compatibility. Meaning new code can read old data. And forward compatibility. Meaning old code can read new data without crashing.
So the format you choose needs to handle both of those gracefully.
Exactly. And as we will see, some formats are amazing at this. And some are disasters waiting to happen. Let us start with the easy option. The one that feels obvious, but is actually dangerous.
Okay, so what is the simplest way to encode data? Like, the obvious thing.
The obvious thing is your language's built-in feature. Java has Serializable. Python has pickle. One line of code. And your object is bytes. Done.
That sounds incredibly convenient actually. What is the catch?
The catch is huge. First, it is tied to your language. Your Python pickle data. A Java service cannot read it at all. You are locked in forever.
Okay, that is bad. But what if my whole system is just one language?
Still bad. Because versioning is a nightmare. And Python pickle can execute arbitrary code when you decode it. It is a massive security hole. Never use pickle from untrusted sources. 3 reasons these built-in formats fail you. Let us go through them.
Okay, so security. Language lock-in. What else is bad about these built-in formats?
Third problem. Versioning. These formats are terrible at it. If you add a new field to your class, decoding old data gets weird. If you remove a field, things crash. There is no clean way to handle change.
So basically, language-specific formats are fine for a quick script. But for anything serious, they are out.
Completely out. You would not build a house on sand. Same idea. Use them for nothing you care about. Language-specific formats. Locked to one language. Security risk. Terrible versioning. Do not use in production. Period. Quiz time. Let us see if that sunk in. Your teammate is using Python pickle in production. Why is that a problem? 5 seconds. Think it through. Yes. 3 big problems. Other languages cannot read it. Versioning is messy. And pickle can run arbitrary code on decode. That last one is dangerous. Never unpickle data from an untrusted source. Okay, so language-specific formats are out. Most people reach for JSON. Let us talk about it.
Okay, so language-specific formats are out. What is the go-to for most people? JSON. Right.
Yes. JSON is everywhere. And honestly, for good reason. It is human readable. You can open it in a text editor and understand it. REST APIs pretty much run on JSON.
I use JSON for basically everything. It has worked great so far. What is the downside?
JSON has a few sneaky problems. Let me walk you through them. The first one trips up almost every developer at some point.
Oh, okay. Now you have got my attention. What is the first one?
Numbers. Specifically, big numbers. JSON has no real integer type. Everything is just number. And that causes a silent, terrifying bug. The number bug. This one has caused real production incidents at major companies.
What is the number bug? JSON supports numbers just fine. Does it not?
Here is the thing. JavaScript uses 64-bit floats for all numbers. That means it can only represent integers exactly up to about 9 quadrillion. Sounds like a lot.
9 quadrillion feels like more than enough for like any normal app.
Twitter hit this exact limit with their tweet IDs. Their IDs got bigger than JavaScript could handle precisely. So JavaScript rounded them. The ID in the JSON and the real ID no longer matched. Tweets disappeared. It was chaos.
Wait. Seriously? Twitter had to fix their IDs because of JSON number precision.
Yes. They ended up sending IDs as both a number and a string. 2 copies. Just to work around this. JSON also has no binary type, no schema, and wastes space. That is a lot of problems. What about XML? It is older, but still very much around. Is it better?
What about XML? I see it everywhere in enterprise stuff. Is it better than JSON?
XML is verbose. Really verbose. The same data in XML versus JSON. XML can easily be 3 to 5 times larger. All those opening and closing tags add up fast.
But XML has schemas, right? Like XML schema definition. Does that help?
It does. And that is actually an advantage XML has. But the schema language is complicated. Most people do not use it. Or get it wrong. JSON schema exists too. But adoption is patchy.
So both JSON and XML are human readable. Both have weaknesses. What is the alternative?
Binary encoding. That is where things get interesting. It is smaller, faster, and it forces you to define a schema, which turns out to be a feature, not a bug. Quiz time again. Twitter IDs. What is the safe way to send a huge number in JSON? Tweet IDs are huge 64-bit integers. How do you safely send them in JSON? 5 seconds. Yes. Twitter literally does this. They send tweet IDs as both a number and a string. The number is for backend clients. The string is for JavaScript. 2 fields. Elegant solution. Why go binary? 3 reasons. Let us walk through them.
Okay, so binary encoding. If JSON works, Why switch to something humans cannot even read?
3 reasons. First, size. Binary is way smaller. A JSON payload might be 100 bytes. The same data in a binary format might be 30. That difference is enormous.
Smaller means faster over the network and cheaper bandwidth. What is the second reason?
Speed. Parsing binary is much faster than text. You are not searching for quote marks. You read a fixed number of bytes. You know exactly what field you are looking at.
And the third reason?
Schema enforcement. With binary formats, you must define a schema. That schema becomes the contract. If something does not match, it fails loudly, not silently. No more mystery bugs. Starting simple. MessagePack is JSON smaller. Binary cousin.
What is the simplest binary format to start with? Like. The easiest to understand.
MessagePack. Think of it as JSON, but binary. Same structure. Same idea. But instead of quotes and braces, it uses bytes. The field names are still there, just encoded compactly.
How much smaller does it actually get?
Roughly 30 to 40% smaller than JSON. Not dramatic, but meaningful. Redis uses a variant of MessagePack internally. Dozens of languages have libraries for it.
But field names are still included in each message. That still seems wasteful.
Yes. That is the key insight. The really efficient formats replace field names with numbers. Tiny little numbers. That is where the real savings come from. Protocol buffers. Made by Google. Used by everyone. Here is how it works.
Protocol buffers. I have heard of Protobuf. Google made that, right?
Yes. Google made it. You define your data structure in a schema file, called a .proto file. Then you run the compiler. It generates code in your language.
So the schema comes first. You write that before any code.
Schema first. Yes. And here is the key thing. Every field gets a number. A tag. Like. User ID is field 1. Name is field 2. That number goes in the binary data, not the name.
So instead of writing the word name, you just write the number 2.
Exactly. And the number 2 takes just 1 byte. The word name takes 4. Multiply that by 1,000,000 messages. You are saving gigabytes. And those numbers unlock schema evolution. Let us look at what an actual Protobuf schema looks like in real life.
Can we see what an actual Protobuf schema looks like? Like the real syntax.
Here it is. A real Protobuf schema. See those numbers on the right. 1, 2, 3. Those are the field tags. The actual names only exist in the schema file. They are not in the binary data at all.
And required versus optional versus repeated. What do those mean exactly?
Required means the field must always be there. Optional means it can be missing. Repeated means it is a list. And I will tell you a secret. Required is actually dangerous. We will talk about why. Quiz 3. Protobuf field tags. What are they actually for? Every Protobuf field has a number like equals 1, equals 2. What is that number actually used for in the encoded binary? Yes. That tag number appears in the binary data instead of the field name. This makes Protobuf compact and enables safe schema evolution. Now, the magic of schema evolution. How do you add a field without breaking anything?
Okay. So field tags. How do those actually help when you change your schema?
Let us say your schema has fields 1, 2, 3. You want to add phone number. You give it tag 4. You never reuse an old number.
Okay. Now new code writes data with field 4. But old code receives it. What happens?
Old code sees tag 4. It does not know what that is. So it ignores it. No crash. No error. This is forward compatibility. Old code skips fields it does not understand.
That is smart. And what if new code reads old data?
New code reads the data. Field 4 is just missing. If it is optional, that is fine. Default value is used. Backward compatibility achieved. New fields must always be optional. What about removing a field? 3 golden rules you must never break.
What about removing a field? Can I just delete it?
Yes. But with one rule. You can only remove optional fields. Never remove a required one. If old code still sends it, new code will just ignore it. Safe.
And can I reuse that tag number for a different field later?
Never. This is super important. Once a tag number is used, it is reserved forever. If you reuse the tag, old data is misread as the new field. Silent data corruption.
So new fields must be optional. Never remove required fields. Never reuse tag numbers.
Exactly those 3 rules. Remember them. Violate any of them and you are looking at a production incident. Why is marking fields as required actually a trap? Let me tell you the story.
Wait. You keep saying never add required fields. But required sounds like a good thing. Validation.
It sounds good. But here is the trap. You deploy new code adding a required field. Old clients are still running. They send messages without it. New code crashes.
So required fields break backward compatibility during a rolling deploy.
Exactly. In Proto 3, every field is optional by default. The Protobuf team admitted required was a mistake. That is a big admission from Google.
Honestly. You make everything sound so clear. I have been confused about Protobuf for years.
You always ask the perfect question. Leo. Now. Thrift. Made by Facebook. Almost identical to Protobuf. Different syntax. Same idea. 2 options. Both solid. Quiz 4. Schema evolution in practice. What is the safe move? You need to add a phone number field to your Protobuf schema. Old clients are still deployed. What is the safe way to do this? Perfect. Optional means old clients can keep sending messages without that field. Always optional for new fields. Now. Avro. The one that breaks all the rules. And somehow works better because of it.
You mentioned Avro earlier. What makes it different from Protobuf?
Avro is completely different. No field tags. No field IDs. In the binary data, there is just values. One after another. No labels at all.
Wait. If there are no tags, how does the decoder know what it is reading?
The decoder uses the schema. The schema tells it. First value is user ID. Second is name. This makes Avro incredibly compact. Sometimes smaller than Protobuf.
So both writer and reader need the exact same schema. Or everything breaks.
Not quite. The writer uses one schema. The reader uses another. And Avro resolves the differences. This is the writer schema versus reader schema magic. Writer schema versus reader schema. Here is how the magic actually works.
Okay, I never understood this. Writer schema versus reader schema. How does it work?
Imagine the writer has version 2. With a new field. The reader has version 1. Avro compares them. Field is in writer but not reader. Reader ignores it. Field in reader but not writer. Reader uses default.
So the reader schema has default values for new fields. Always.
Yes. In Avro, a new field needs a default value. No exceptions. Otherwise, reading old data will fail. Avro is very strict about this. Writer has new field. Reader does not know about it. Avro resolution matches them up. Perfect. How does Avro know which schema was used? That is the clever part.
Okay, so if Avro needs both schemas, how does the reader know which schema the writer used?
In a large file, Avro writes the writer schema once at the beginning. Every reader of that file knows the schema. Simple.
Okay, but what about individual records over a network? You cannot attach the full schema to every message.
Great point. You use a schema registry. Every schema gets a version number. The writer includes just the version number in the message. 4 bytes. The reader looks up the full schema. Huge benefit.
That is actually pretty elegant. A registry that everyone points to.
Confluent Schema Registry does exactly this for Kafka. It is a standard pattern. You store schemas centrally. Avro becomes really powerful here. Quiz 5. Avro and backward compatibility. What is the rule? You add a new field to your Avro schema. Old data was written without it. What do you need to do to keep backward compatibility? Yes. The new field needs a default value. When Avro reads old data, it falls back to the default. Backward compatibility maintained with just one rule. Now let us zoom out. There are 3 ways data actually moves between systems. Each one works differently.
Okay, we talked about the formats. JSON, Protobuf, Avro. But how does data actually move between services?
There are 3 main ways data moves. Through databases. Through services, like REST. And through message queues. Each one has different compatibility rules.
Starting with databases, I guess. That is the oldest one.
Databases are like a time machine. You write data today. 5 years from now, some new version reads it. That old data needs to still work. 3 ways data flows. Via databases. Via services. Via async message passing. Each one has its own compatibility rules. Databases. The time machine problem. What can go wrong during a migration?
The time machine analogy is good. But what actually breaks in a database when schemas change?
You add a new field to your database. Old rows do not have a value. The database fills it with null. New rows have values. Old rows have nulls. Both exist at the same time.
Okay, but if old code reads a row written by new code, it sees a column it does not know. What happens?
If old code reads it, processes it, and writes it back, it does not know about the new field. So when it writes, the new field value is gone. Silently deleted.
So old code can silently destroy new data by just updating a row. That is terrifying.
This is why database migrations need to be careful. Do backward compatible migrations only. Add columns. Never delete them while old code is still running. Quiz 6. Database Dataflow during a rolling deploy. What happens? You add a new column during a rolling deploy. An old code instance reads a row, updates it, writes it back. What happens to the new column? Yes. This is the danger. Old code only writes the columns it knows about. The new column might be silently dropped. This is why careful migrations matter. Next. Data flow through services. Starting with REST. The one you use every day.
Okay. Next up is data flow through services. I use REST APIs every day. What about encoding there?
REST stands for Representational State Transfer. It is a style, a set of rules. You use HTTP verbs. Get to read, post to create, put to update.
And resources are identified by URLs. Like /users/123.
Exactly. And REST APIs usually use JSON. Great for public APIs. The compatibility story is simple. Add new fields to your JSON. Old clients just ignore them. Nice and clean.
That sounds really simple. What is the alternative to REST then?
RPC. Remote Procedure Call. And it is the one that trips up a lot of engineers. Because of a fundamental lie in its design. RPC. It looks like a function call. But it is not. And that is the problem.
What does RPC look like? And what is this lie?
RPC tries to make a remote service look exactly like a local function. No URLs. No HTTP verbs. Just a regular function call. Simple. Right.
That does sound simpler than REST actually. So what is the problem?
The problem is, it is a network call pretending to be local. And networks fail. The function can time out. The network might deliver the request twice.
So by hiding the network, RPC gives you false confidence.
Exactly. You need to handle timeouts, retries with idempotency, things you never think about with local functions. gRPC is much better, but it is still a network call. Quiz 7. gRPC and duplicate requests. What goes wrong? A network issue causes a gRPC request to be delivered twice. What is the problem this creates? Yes. If the operation is not idempotent, like charging a credit card, delivering it twice means you do it twice. You must design operations to be idempotent. Third and final mode. Message passing. The async way. This one is my favorite.
Third mode of Dataflow. Message passing. What is that about?
Message passing is async. You send a message and you do not wait for a response. The message goes to a broker. The receiver picks it up whenever it is ready. They are completely decoupled.
So if the receiver crashes, messages do not get lost. They wait in the broker.
Exactly. That is the superpower. The broker holds the messages. Receiver goes down. Messages wait. Receiver comes back. It processes them. Horizontal scale for free.
That sounds incredible for high volume stuff. Like sending emails.
Perfect examples. Order created. Send to queue. Email service sends the email. Inventory service updates stock. All from one message. Zero coupling. Kafka. The broker that changed how we think about events. Here is what makes it special.
I keep hearing Kafka everywhere. How is it different from a regular queue?
Traditional queues delete messages after they are consumed. Kafka does not. It keeps messages in a log for days or weeks. Any consumer can replay old messages anytime.
So I could add a new service tomorrow and replay all events from last month.
Yes. This is Kafka's biggest selling point. Point it at Kafka. Tell it to start from the beginning. It catches up on everything. You can backfill data for free.
And for encoding in Kafka, what format do people usually use?
Avro is the most popular choice. With the schema registry, each message includes the schema version ID. The reader looks up the schema. Small. Fast. Schema evolved. Beautiful. Quiz 8. Message passing. Which system lets you replay months of history? Your analytics team needs to backfill 6 months of historical order events. Which system makes this easiest? Yes. This is exactly what Kafka is built for. Kafka retains messages. The new service just sets its offset to 6 months ago and reads forward. Now let us put it all together. When do you actually use each format?
Okay, so JSON, Protobuf, Avro, REST, Kafka. How do I decide what to use?
There is a simple framework. Is this a public API? If yes, use REST with JSON. Clients are external. Human readability matters more than efficiency.
And if it is internal, like microservices talking to each other?
For internal services, use gRPC with Protobuf. You get type safety. You get the compact binary format. Huge developer experience win.
And for events, when one service needs to tell others something happened,
Kafka with Avro and a schema registry. The decoupling is worth the complexity. You can add new consumers anytime. This is event-driven architecture done right. Summary table time. Screenshot this. Use it every time you pick a format. Here is your quick reference. JSON for public APIs. Protobuf for internal services. Avro for data pipelines. Done. This table has everything. Format. Whether it is human readable. Does it need a schema? How big is it? And when to use it?
This table alone is worth the whole episode. Seriously. Everything laid out perfectly.
3 things to remember. 3 things that will change how you build systems forever.
Okay, if someone asks me to summarize this chapter, what do I say?
3 things. 1. Every encoding format is a trade-off. Public API. JSON. Internal. Binary. Pick based on your context. 2. Schema evolution has rules. New fields must be optional. Never reuse tag numbers. Follow these and you will never have a compatibility incident. 3. How data flows changes everything. Databases need backward compat for years. Async messaging lets services evolve independently. Match encoding to Dataflow mode.
Aria. Honestly, you make everything click. Also, I may have a small crush on how you explain things.
Leo. That is very sweet. But focus. Save the crush for after the episode. We have an outro to do. Episode 5 is coming. And it is going to make you question everything you know about databases.
What is coming in episode 5? I am already excited for it.
Episode 5 is replication. How do you keep the same data on multiple machines at once? And what happens when they disagree?
Philosophically wild. For a database episode. Now I am very curious.
We will talk about leader and follower replicas. What happens during a failover? The nightmare scenario where two nodes both think they are the leader.
Two nodes both thinking they are in charge. Sounds like my last team meeting, honestly.
Ha! More relatable than you would think. Subscribe so you do not miss it. And now, I believe we have an outro to get through. Leo. If this helped you, smash that like, hit subscribe, and share it with one friend who is learning system design. It genuinely means the world. See you in episode 5. Episode 4 complete. See you in episode 5. Replication, here we come.